Thanks for coming, everybody. This is a continuing joint effort between IFML, the Institute for Foundations of Machine Learning, and UT's Good Systems project that is concerned about AI and its application to real world problems, and also its sort of the ethical implications of AI. So both IFML and Good Systems are interested in that. We're trying to collaborate. And as part of that, we have a joint seminar series going on, and we have both external and internal speakers. And so today we have Maria De-Arteaga, who's a new professor in the business school here at UT. She's in the IROM department. And Maria got her PhD, as we were discussing, in Pittsburgh from Carnegie Mellon University in both machine learning and public policy. She's won many awards for her research, and she also co-founded the Machine Learning for the Developing World workshop series at Europe's. So we're very excited to have her here and to get her perspective. So thanks for being here, Maria, and you have the floor.
Thank you very much for that introduction, and thank you all for coming. Today, I'll be talking to you about minding the gap between predictions and ML-informed decisions. And these are my wonderful collaborators for the works that I will be presenting to you today. In recent years, we have seen an increase in the use of machine learning to assist experts in making high-stakes decisions, ranging from healthcare, human resources, to child welfare. And throughout these, there's typically a focus on the locus of evaluation being the machine predictions. And in particular, this is typically done in constrained and static evaluation settings. And so we have headlines like AI system is better than humans at making predictions, or a system just beats a human at making predictions. And when we're doing these, our focus is on the algorithm, the data, the outcome that we're predicting, what is the objective that we're optimizing. But typically, what we care about when we're making predictions to inform expert decisions is the decision itself, not the prediction. And this adds a lot of complexities to what we care about. In particular, we care about the fact that we're translating a complex real-world objective into a quantifiable objective. We care about the fact that how the human may be making that decision and incorporating that decision into their assessments may not be uniform across the space. And the incentives that the human has may influence how they make use of the predictions. And before I go ahead, isn't full automation a matter of time? In case anyone's thinking, well, you know that it's just for a couple of years that we have that issue before we've just fully automated everything and gotten rid of the experts. And not really. There's certain cases where, for instance, often decisions are not solely based on predictions. There are decisions that even if we had a perfect prediction, the grounds for the decision are not just the prediction itself. In the criminal justice system, even if we had a perfect prediction, we're not only making decisions based on a prediction of future behavior, but also on what happened in the past. And naturally, there's certain constraints to how well we can do in that prediction when we're dealing with prognostic tasks that concern future human behavior, rather than diagnostic tasks, where we can actually assess some notion of a ground truth that we know we're trying to be estimating. And when it comes to that ground truth that we're trying to be estimating, there may be conflicts in what is that objective that we care about, and what we care about may not be something that we can perfectly quantify. So with these, in today's talk, I will focus on two things. In the first part of the talk, we will focus about the gap that exists between predictions and decisions. And in particular, in the question, are humans capable of making good use of algorithmic recommendations to improve decisions? The idea that we want a human in the loop is grounded on the fact that we say, well, that human is going to be making good use of the prediction, and everything that I just said, that there are objectives that may not be entirely quantifiable. We may want the human to incorporate unobservables. Well, are humans actually able to do this in any way? And so the first portion of the talk will focus on this. The second portion of the talk will focus on the gap between the measured construct and the relevant construct. And in particular, I'll be looking at how do we bring the constructs that we optimize for closer to the relevant constructs. The first part will be more of a within CS context, what you would term HCI, in other settings, what you would term more behavioral. And the second part will be more centered on the machine learning components. So for the first part, we're wondering whether humans are capable of making good use of algorithmic recommendations. We can frame this question in terms of algorithm aversion and automation bias, which we can understand as two ends of a spectrum of how humans make use of recommendations provided by an algorithmic system. Algorithm aversion refers to under-compliance. This phenomenon leads humans to disregard the machine, even when their recommendation may be providing useful information that could improve the quality of their decisions. And in particular, researchers have typically observed this in the context of humans dismissing the algorithm in favor of another human that is less reliable, but they perceive as a better source of information. On the other end of the spectrum, we find automation bias, which results from overcompliance. This is what was found, for instance, in the context of high-tech cockpits when they were first deployed, and researchers found that pilots were now less vigilant to certain cues that they tended to be better at identifying before the deployment of these systems, because they were over-relying on the algorithm, or on, in this context of high-tech cockpits, on the new technology. So we can refine the question in part one to, are experts able to dismiss algorithmic recommendations when the tool misestimates the risk? And we will be focusing on the child welfare context. Algorithm-assisted decision-making often takes the form of a risk assessment instrument that estimates the likelihood that a person or case will have poor outcomes. And this is widely used in lending, criminal justice, healthcare, child welfare, and is increasingly being deployed more and more. In the context of child welfare, it is estimated that 37.4% of children in the US experience a Child Protective Services investigation by the age of 18. And the statistics associated to this is there's approximately 4.3, this from 2018, 4.3 million referrals, so calls, and 7.8 million children were associated to these calls. One call may refer to multiple children. And as a result of these calls, 3.5 million children received investigation or alternative responses. In our work, we study what happened when the algorithmic risk assessment system was deployed in Allegheny County, the county where Pittsburgh is located. This is an overview of the call worker's decision-making process prior to the deployment of the tool. So the call worker has access to the information communicated to them in the call and to administrative data records associated to the children and adults involved in the call. Based on this information, they're tasked with deciding whether to screen in or screen out the call. If the case is screened in, an investigation is open, a social worker visits the home, and different outcomes may take place, such as services being offered to the family or the child being placed out of the home. If the case is screened out, no investigation is open, meaning we do not observe any outcomes. The high volume of calls means that not every call is investigated, and the information communicated in the call may often be inconclusive. Because there's a high risk of false negatives, meaning failing to investigate a case where the child was indeed in danger, child protective service agencies have made increasing efforts to increase the amount of information available to the call worker, such as criminal history of the adults involved in a call. And in turn, this led to an explosion of information. And so now call workers had access to something like 800 variables that they could look at when they received a call, which meant that they couldn't easily parse this information. This in turn led agencies to look into deploying algorithmic risk assessment tools that could help summarize this information to call workers in the form of a risk score. And many local agencies are hopeful that this will reduce the number of high-risk cases that are missed. In the meantime, others have expressed concern over the increased deployment of these systems. For instance, the National Coalition for Child Protection Reform published a commentary titled "Pittsburgh's Child Welfare Agency Goes Full Orwell." So the way that the risk assessment tool, the deployment went was the predictive model is a predictive model that provides a risk score from 1 to 20, where high risk scores indicate higher risk. And it additionally flags some cases that are estimated to be at high risk of out-of-home placement. For these cases, the call worker requires a supervisor's approval to screen out the call. So if they don't think that this call should be investigated, they need a supervisor's approval to screen it out. And call workers still have access to the historical records. And importantly, the predictive model is only estimating risk based on historical records, not on the information communicated in the call. So with this, we revisited a question that is, are call workers able to dismiss algorithmic recommendations when the tool misestimates the risk? And I like telling you what the findings are up front. So what we will find is that in this case, we found that call workers often did alter their behavior when using algorithmic recommendations, meaning they didn't fall on the end of the spectrum or full algorithm aversion, but they were less likely to adhere to recommendations resulting from misestimated scores, meaning they weren't victims of automation bias. So the timeline of the data that we have is we have data from before that was used to train the model. So the model development data was data that was from before July 2014. We also have data from pre-deployment between January 2015 and August 2016. That is what we term pre-deployment. This is data that was from a period of time where no algorithm was being used, but it's also data that was not used in the training of the algorithm. And then we have data post-deployment, when we observe how the decisions changed when the tool was deployed. So a little bit more information about the predictive model. So the covariates that the algorithm uses are the administrative records. So this is just the historical information associated to children and adults involved in a call. It predicts two outcomes: out-of-home placement and future referral, which is a future call concerning the child. And the output that it provides is a risk score from 1 to 20. So basically the probabilities are then bucketed into 20 scores, and then the maximum of these two scores is shown as the risk score, the maximum of the two possible outcomes. And then a supervisory approval is required if the probability of the risk score associated to out-of-home placement is greater or equal than 18. When the system was deployed, they didn't realize that there was a glitch in the tool, which is what allowed us to study how the coworkers behave when the score is misestimated. Some features were miscalculated in real time, which led to misestimated scores. Importantly, the call workers, when and if they tried to look at the original features, they would look at the real values of the features. There was no glitch there. The glitch happened when the covariates were being fed into the predictive model. So as a result, what we're seeing here is x-axis assessed score. So that is the score that would have been the correct score, basically, if the features hadn't been misestimated in real time. So we calculate this retrospectively. And the shown score is the score that coworkers actually saw. As you see here, there's a very strong correlation. For a lot of these are aligned. It wasn't a random score that was being shown, but 17% of shown scores were miscalculated by 5 or more points. And many cases that should have been flagged as mandatory screening were not. Importantly, this allows us to see how this effect of the mandatory screening supervisor's approval required affects things. So the first question that we want to ask is, well, did something change before and after the model was deployed? Or did they simply ignore the recommendations? What we're seeing here, we compare the behavior of coworkers in the pre and post deployment periods. So since we're not able to retroactively reproduce the glitch to get pre-deployment shown scores, we cannot see what would have been the shown score with the glitch for data that was before the deployment of the tool, because we cannot reproduce the glitch. In the plot on the right, what we compare is the screening rate across values of the assessed risk score for each of the 2 periods. If the deployment had not influenced the behavior of coworkers at all, then we should observe that the screening rate for each level of the score should not change. However, we see that the steeper slope of the post-deployment curve, particularly for very high and very low risk cases, indicates that post-deployment screenings are better aligned with the score. We see both a pronounced increase in the screening rates of highest risk cases and a pronounced decrease in the screening rates for low and moderate risk cases. And likely due to resource constraints, the overall screening rate did not vary in the 2 periods and remained constant at 45%. And by the way, we also checked that there was no significant change in the population of children or the county's policies. So this change in the alignment can be attributed to the deployment of the tool. After the tool was deployed, the question is then, so basically what the analysis that I just showed means is that there was no algorithm version in which they were entirely dismissing the algorithm and working as if the scores weren't there. But then how were they using the scores? And in particular, are coworkers able to dismiss algorithmic recommendations when the tool misestimates the risk? Or did they blindly follow the recommendations, meaning automation bias? So here what we're looking at is the behavior of coworkers in the presence of the glitch in the post-deployment period. In this plot, we compare screening rates for assessed and shown scores. We again can see that the human decisions are better aligned with the assessed score than with the shown scores. In particular, screening rates are higher for very high values of the assessed scores than for those of the shown score. And if you look at the relatively high screening rates for cases with very low shown score, which is approximately 30%, this suggests that the coworkers are effectively using other information at their disposal to avoid making errors of omission. So basically what we're seeing here is that the coworkers are better aligned with the assessed score. And in particular, when we look at the low scores, this indicates that the coworkers are either using the information in the call or the features themselves to make different choices in cases where the risk score alone would suggest that they should not screen for investigation. But we're also interested in distinguishing the behavior of coworkers in cases of under and overestimation. So this is what I'm showing you here. So this plot shows you the percentage of screenings for a bin version of the shown score. So here, correct indicates that the assessed score is equal to the shown score. Underestimation means that the score shown was lower than the assessed score. And overestimation means that the score shown was higher than the assessed score. It was an overestimation. So if the co-workers were blindly following the risk score, we would observe that within each score bucket, the screening rates are the same across all three cases, because from the basis of the score shown itself, these would be undistinguishable. But what we observe is something very different. Among cases with similar shown scores, cases for which the score was underestimated are screening at a much higher rate than the others. This means that humans are at the aggregate level able to identify that the risk is being underestimated for these cases. And let's look at a particular bucket to get a better idea of what we're seeing here. So for the cases with a shown score between 11 and 15, those for which the score was an underestimation of the assessed score were screening at a rate of almost 60%, while the other cases with a shown score in this same range were screening at rates around 30%. So again, this suggests that the co-workers make use of other pieces of information, either from the call or the administrative data, and respond appropriately by screening in with higher probability. And finally, well, this doesn't differentiate between the different magnitudes of the misestimation, right? It's different if the misestimation is by 5 points or by 12. So what is going on when we consider the magnitude? So here we're looking at the cases with assessed mandatory screening. So these are the cases that, the proportion of cases with assessed mandatory screening that were actually screened in for each bucket of shown score. So these are cases assessed mandatory screening would mean that they should have received a flag that says you need supervisor's approval. Only those with a score shown of 18 to 20, roughly, because the flag is calculated just on one of the two outcomes, so this is not a perfect one-to-one match, but only those would have received this mandatory screening flag. So we should see, if this is just the only thing that is having an effect, that those are the ones that they screening higher. However, what you can see is that the screening rate is approximately constant across all buckets. And this suggests that the underestimation of the assessed score had virtually no effect on the co-workers' actions for these very high risk cases. So even when the shown score was more than 12 points lower than the assessed placement score, the screening was still as likely as for shown mandatory cases.
Hey, Maria, can I ask you a quick question?
Yeah.
Do you have a feeling, can you tell us which features are being miscalculated or misestimated more commonly? Like, you know, does that indicate, give any light on the discrepancy here for that?
We tried to reconstruct the glitch, and I have some, actually, I don't think I have them here, unfortunately. We do have some plots showing what the misestimation is, but basically the long story short is it's a little bit of a mess in terms of there's a lot of features that are misestimated, and whether some features are more likely to be, some features are populated by zeros when they shouldn't be, but some features that should have been zeros are populated sometimes by non-zeros. So there is not really a very clear pattern to what the glitch was, because that was definitely one of the things that we tried to do was reconstructing the glitch.
Okay, so it was fairly uniform, the errors in the features.
I wouldn't call it uniform. So that's one of the things that is, we cannot say that the glitch was randomly assigning cases, because some features were not miscalculated. So basically what it means is we cannot make a clean analysis of, look, this was the glitch and this is how this feature is affecting things. But we also cannot claim, well, this risk is random and this glitch is just randomly sometimes miscalculates and sometimes it doesn't in entirely random ways. It's just the pattern is complex enough that we're not able to clearly identify it.
Got it.
As long as there's a question, maybe I can ask one as well. So So in some sense, we're very lucky, and you were very lucky that there was this glitch, right? That allows you to do this analysis in an actual high stakes decision, and you're making a really interesting finding here that in some sense should open up a whole new, sort of batch of studies on, does this apply in other high stakes decision scenarios? But to actually get data like this in any other high stakes decision would presumably be unethical. So what can we generalize from this, given that we can't really replicate the study in any way, or are there ways to replicate?
No, absolutely. This is a great point. And this takes me actually to the next slide, that is what the findings are. And importantly, what can we draw from this, right? That is, as you point out, this study has the advantage of having inherent field validity. And so this means that we're able to draw conclusions of how humans were actually using this tool in a high stake settings. So this is something that we couldn't have done a randomized experiment, because it is highly unethical to say, well, let's pretend we tell this person that this is a low risk case, even though we estimate that it's a high risk. And lab experiments, in which we could even do it with the co-workers themselves, in which we say, well, we simulate a setting in which you are making these decisions. The nature of the task, the fact that these are high-risk decisions in which the co-worker knows that there is a child whose life is potentially at risk, may change their behavior when they're in a lab and they're saying, well, this is the way that I'm supposed to be making these decisions, versus when they're actually in the field and they're faced with these decisions. So the main value of this research is that it allows us to conclude something about how humans are using the tool with inherent field validity. And the importance here is that we see that this desirable behavior of humans are more likely to adhere to recommendations that result from correctly estimated scores, right? This means that while algorithm aversion and automation bias are real phenomena that we need to be concerned about, that doesn't mean that humans cannot make good use of these algorithms. So I think that the main lesson that we take from this is this desirable behavior that drives us to think, okay, we want to have humans in the loop, and we want the human in the loop to have certain tasks, is something that is reasonable to strive for, because we have seen that it can occur. However, we don't know what was it about this system that led to this positive behavior. So the thing that is missing, and where I think that more controlled experiments can provide important insight, is what are the elements of the design of these that led to this positive behavior? Was it the fact that the coworkers had access to the raw features? Was it the fact that the coworkers had a very clear understanding of what the score was and was not calculating, and what the algorithm was and was not seeing? So in Virginia Eubanks, to this question, in Virginia Eubanks' book, where she's talking about the Allegheny County tool, there's this portion where she talks about how she's interviewing a coworker, and the coworker perfectly estimates what the algorithm is going to say. And that, in my reading of it, shows an understanding of what the algorithm, what are unobservables to the algorithm, what is the objective of the algorithm, that may be one of the elements that may lead them to make good use of this score. So to summarize, the advantage is inherent field validity. We know that this desirable behavior can happen. The next step is, what is it about the study design that led to this positive behavior? And for that, we do need to have more controlled experiments, potentially in lab settings.
Hey, Maria.
Yeah.
So two chat questions here. So one is, well, I guess maybe this might be better to take at the very end, but have there been any attempts to figure out why they didn't adhere to the recommendations from misestimated scores? And then have you or anyone on your team collected a folksonomy of call workers' characterizations of their overriding the algorithm?
So in this study, we didn't do any surveys with the co-workers or any studies of focused on the why was it that they were behaving one way or the other. This was purely looking at the patterns that we observed, but there are others working in this space that are looking at these type of questions. And I think that I totally agree that that is a really useful source of information that, in addition to more controlled studies, definitely gaining insight into how the co-workers are making use of the recommendations through other approaches can be very valuable.
Thanks.
Of course. Okay, so with these, if there are no other questions, I will move to part 2 of the talk, in which we will be focusing on how do we bring the constructs that we optimize for closer to the relevant constructs. So the first challenge, there's 2 challenges that I'll be discussing on what is it that is being optimized for and what is it that we actually care about. So there's a selective labels problem in which, as I said, only calls that are screened in for investigation have an observed outcome. And so what this means is that rather than estimating the probability of y given x, you're estimating the probability of y given x and d equal to 1. And while this is typically addressed with approaches such as inverse probability weighting and similar methods, there is a challenge to doing these under unobservables, and Lacaraju and her co-authors have characterized this. And because in this context, unlike other sample selection bias contexts, there is a very intimate link between the source of the selective labels and what we're trying to predict, meaning the human is trying to predict something very closely to what the observed outcome is. If there is partial human consistency, then we will have a violation of the positivity assumption, meaning there's a portion of the feature space for which we don't observe any labels. And in addition to this, we have the omitted payoff bias. What this means is what we optimize for in machine learning is typically a measurable but flawed proxy of what we care about. In this context, the machine is optimizing for what is the probability of out-of-home placement, whereas what the human cares about and what we care about in this task is the child at risk? Not all cases where the child is at risk result in out-of-home placement. And that is a good thing, right? Out-of-home placement is an outcome that, to the extent possible, Child Protective Services tries to avoid. So the second part refined is, can we learn from experts' decisions whenever they display certainty and consistency, and learn from observed outcomes otherwise? So the intuition here is experts have a wealth of expertise. And in the context of, if you go to the doctor, for instance, there are many cases that are easy for doctors to diagnose. They have enough knowledge to give you a very accurate diagnosis, whereas there's others where there may be a lot more uncertainty, a lot more difference in opinions. And so can we learn from those subsets where humans are consistent, which, by the way, are the ones that will lead to violation of the positivity assumption under selective labels problem, and then learn from observed outcomes elsewhere. So this is naturally inspired by wisdom of the crowds context. The challenge here is that when you're collecting data by asking a lot of people, you can directly observe whether they agree or they disagree. In the context of learning from historical expert decisions, we have a single decision per case. And it is often unfeasible to say, okay, let's start asking a lot of co-workers for what their opinions are, or let's do an experimental setup in which we collect this data, because they are already under so much strain in the system. And so the question is, how can we estimate consistency across experts when a single expert assesses each case and there's a no run, sorry. there's not a random assignment of cases to experts, meaning the person who works on the weekend may observe very different cases than the person who works on a weekday at noon. So on a weekday, you may be receiving more calls from teachers, whereas on a weekend at night, you may be receiving more calls from family members and from neighbors. So the proposed approach is to model the human decisions with machine learning to identify consistency, and then use influence functions to identify whether their consistency is across experts. And finally, use label amalgamation to incorporate the inferred consistency into the labels. And throughout, the underlying assumption is that consistency across experts is indicative of correctness. This is reasonable in some instances because experts are experts. So there's something that we can derive from whenever they're all in agreement with each other. However, this has a problem that when dealing with societal biases that may be shared by a group of decision makers, then this could lead us to incorrectly interpret shared biases as expertise. So what we have is we have the data, and we have the covariates X, we have a decision for each case, and depending on one of the decisions, we have an observed outcome, Y. The first thing that we can do is we can build a predictive model to predict the human decisions. In the examples that I'll show you, we're using a simple logistic regression. And from this, if the estimated probabilities are calibrated, you can obtain a high consistency set. So this is a set in which you're predicting with very high probability the correct decision. The question here is, are high probability predictions reflective of consistency across experts? Or is it just that you have a non-random assignment of experts to cases and there is one expert that assesses a set of cases, and so you're just predicting very well what the decisions of this single expert will be? Is there a question in the chat? I can, sorry, go ahead.
Is there a lot of variability among participants trusting the algorithm? It seems like willingness to trust the algorithm could be a personality trait regardless of the setting.
Yeah, so here we're looking at learning from historical decisions before the tool was deployed. So this is for this part. If it's related to the first part, then yes, there may be variability. We also tried to look into that, but the problem is that because co-workers work under one supervisor and the supervisor may be influencing how they're making decisions, then you can't really assume that the decisions are independent from each other.
I have one other related question. So do we know what other data these users might have, right? Because I guess consistency sort of tacitly assumes that you know, the features that we're currently encoding in this matrix are all of the information that the decision makers might have had.
Yeah, that's a great question. So we don't, and one thing that we know is that they have access to other information, right? Because they have access to the information in the code. The thing is that if the information that you have is not sufficient to predict the decisions, if for instance, they're making use of the information in the code to make different decisions for cases that look identical to us according to the information that we have, then you're not going to be estimating a high consistency for these cases, because you're effectively going to be doing a poor job at predicting. And so what you're going to be saying is, well, I can estimate that here the probability that you'll make this decision is 50%, because from the data that I observe, half the times you do one thing, half the times you do the other thing.
Okay, great. So you're just saying that like this is consistency with respect to the set of features which are currently in the matrix, which you're sort of necessarily inconsistent in decision making with respect to those features if you're relying on other features which are not visible to that.
So basically what we're saying is that, so if you want to interpret all of your probabilities as indicative of consistency, then you need to assume that there are no unobservables. But when you focus on the high consistency set alone, that is what we're doing, then you don't have that problem. And our approach won't address nor exacerbate the problem of learning under unobservables, because if you have an unobservable, what you're going to get is that your function f of h cannot get a good prediction for this subset of cases. Because in your data, there's just half the times you go one way, half the times you go the other way, and the piece of information that allows you to discriminate between these two in the statistical sense is not available to you.
Great, thanks.
Yeah, that's a very important question. Thanks for asking it. And so here the question is, well, is the consistency across experts indicative? Is the consistency across experts, or is it just for one expert? And so one way in which we can rephrase this question is, are the high probability predictions influenced by historical decisions of multiple experts? And so to do this, we propose to use influence functions. So influence functions are a technique from robust statistics that allow us to estimate how a functional would change if we perturb the data in a certain way. And by the way, if like there's other ways in which people use influence functions, and so this is basically like the notion of influence functions that you may have seen used in the context of adversarial learning, and originally this is from the 80s from Cook, that is looking at influence functions as a way to estimate perturbations, how perturbations of the data can affect a functional that you're estimating. So we have data, there's only certain things that we care about. It may be the loss function, it may be a predicted probability. And so we care about, under certain perturbations, how will those estimates vary? And in particular, we can say, well, what happens if we perturb the data in the direction of an expert? If we say, well, we upweight the weight given to an expert by epsilon. And so this is equivalent to perturbing the data by in a certain direction. If you think about your data being in a space of, if you have m data points, then you're in an m-dimensional space and you're perturbing it in a direction, by epsilon in the direction that is determined, that corresponds to that expert. And so there you can look at how that influences, for instance, the predicted probability for a new point. And I'll spare you the derivation here. The important point is that we can express it in terms of quantities that can be estimated. Most computationally expensive part here is to compute the inverse of the Hessian, but there are efficient computational methods to do so. And from this, we have the influence across experts. So this is for a given test point, for instance. We have the influence that each expert has over the predicted probability. And in this plot, I'm sorting them according to the magnitude of their influence. So in this example, this point here, this expert here would be going very much in the opposite direction than the other experts. And from this, we can calculate things like the center of mass of this plot, meaning if you have a very small center of mass, it means that one expert has a huge influence, whereas the other ones don't, and the aligned influence, the direction in which the influence is going. So a positive influence means if you upweight the influence given to this expert, your predicted probability is going to increase. A negative influence is if you upweight the weight given to this expert, your predicted probability is going to decrease. And so with this, we can revisit this high consistency set and constrain it to cases in which through the influence, we estimate that this high consistency is robust to variations of the weight given to different experts. With this, we can now obtain amalgamated labels, which are labels in which we say, for those cases in the high consistency set A, we learn from the human decision, we learn from D, and everywhere else we learn from the observed outcomes. And so with this, we can look at, this is what happens in semi-synthetic experiments. So here we just wanted to simulate We look at what happened under very simple assumptions of decision making. So these, and here what we're showing is what happens when you automate the humans, what happens when you optimize for the observed outcome alone, and the proposed approach. And we look at the naive evaluation in gray and the actual evaluation with respect to the construct that we care about. The first, and we look at AUC around their security. So first case, uninformed humans, they're all making random decisions. We're not amalgamating anything. So that amalgamated approach does as well as learning from observed outcomes. If we have oracle humans, then here the best you could do is learn from the humans. And the amalgamated approach incorporates some of this knowledge and does significantly better than learning from observed outcomes. Importantly, that is missed when you do naive evaluation. And this shows us what happens if all humans are oracles, but one is biased against one group that they also have a disproportionate assessment over because of non-random assignment. So you have one human that observes more of one group and they overestimate the risk for that group. Here you're like, well, you kind of do the same. But when you look at that group in particular, you see that when you train a model that it just predicts the human decisions and tries to automate the humans, that model really absorbs the bias of one biased decision maker, while all the other ones may be oracles. Whereas the amalgamated approach is robust to these one bias. A reminder that this is not the case if all the humans share the biases, because then we would be confusing expertise with bias. What happens in the child abuse hotline data? Here, as I mentioned to you, the system is optimizing for out-of-home placement. In the model that I showed you, that deployed model optimized for both out-of-home placement and future referrals. They have stopped using future referrals since because it's tricky to read into what a future referral means. Sometimes there's a neighbor that just calls a lot on someone or something like that. So it's not a very useful signal. That's what the agency assessed. And there are other outcomes that are observed but not used by the deployed model. In particular, they observe whether a call is substantiated, whether a social worker who visited the home says, yes, there were grounds for investigating. And they also observe if services were offered to the family. The reason why these outcomes are not used is because the out-of-home placement is an assessment that comes from an outer source of decision-making. So basically, it's not the agency themselves that makes this decision. And so for the agency, it is important to avoid any self-fulfilling prophecies in their decision, which is why they use out-of-home placement and referrals that are truth signals that don't depend on their processes. For our purposes, this allows us to validate a method that is typically very hard to validate because we're relying on the whole point is that we don't observe what we care about. So in this case, we do observe these outcomes and they're not used by the model. So what we see here is that for out-of-home placement, what the algorithm is optimizing for, the deployed algorithm is optimizing for, the amalgamated approach improves performance with respect to the humans alone, the model that just tries to predict the human decisions. When we look at substantiation and services, and here is still the model that is just going for out-of-home placement does better. But when we look at substantiation and services, we see that the humans have a much higher rates here, and the amalgamated model is able to incorporate this. So basically what we're seeing here is amalgamation is improving performance on other key child welfare outcomes. So to summarize, leveraging inferred expert consistency can allow us to build models that mitigate risks of selective labels problems and omitted payoff bias. And in the case of child abuse hotlines, amalgamation improves performance on other key child welfare outcomes. And overall, what we've seen today is it's important to mind the gap between predictions and decisions. How humans make use of recommendation matters and varies. Algorithm operational automation bias are real, but that doesn't mean that humans always make poor use of algorithmic tools. And there is a gap between the measured construct and the relevant construct. And evaluating with respect to the measured construct can be misleading at times. And in designing ML for decision support, it's important for us to center the relevant construct. And now I would love to take any questions that you may have. Thank you.
Great, thanks, Maria. I'm sure everyone is virtually clapping for that great talk. Any questions?
I think there was a question from Yunfeng earlier.
Yeah, Junfeng had a question here. Junfeng, do you want to jump in here? Well, he asked, I'm wondering how you can do this in a lab setting. Can you ethically do it? I think Peter also sort of alluded to this issue.
Okay, yeah, so here doing it in a lab setting would be easy in terms of, I mean, it's hard to get the co-workers time. And so the challenges here are if it's not co-workers, then it is hard to extrapolate if you're using, for instance, either, I mean, obviously, if you're using something like Mechanical Turk or other workers, whether you can make sure that they would behave like co-workers would behave who have their expertise. There's a challenge in getting the time of co-workers, but assuming we get the time from co-workers, we could then vary specific elements of that system, and then we could be able to study some variations. So we could be able to study whether certain attributes of the tool may make a difference or things like that. There's certain things that I think are not easy to vary in lab settings. So this is not unethical if you're not making actual decisions over the children, but there's certain things that are hard that I think are very interesting to study and not very easy. Like, for instance, is the phenomenon that we found going to remain when the co-workers that started working didn't have experience working without the tool? And so that is something that we don't know if it is the fact that they had so much experience making the decisions without the tool that allowed them to make very good use of it, other sources of information. And are we going to see over-reliance when people start working with the tool? And naturally, we cannot reintroduce a glitch in that case. So those are, I think, some questions that are not straightforward to study in the lab and that I think are very important for what it means in terms of how, for instance, decision makers should be trained to make these decisions. Like, do we need to train them without the tool first before we give them the tool, or does that not matter at all?
So maybe if I can summarize what you're saying, I think you're saying that, I mean, first of all, it's clear the study that you did is fantastic in that it's, you know, it has this field validity. And, you know, it's not in a lab setting, it was real decisions and it just happened. And so it was, you know, it's great. And you're saying, you know, but we can't really replicate that deliberately. And so, you know, to try to understand what happened, then we can conduct controlled setting in a laboratory setting, we can do controlled experiments. But I think, but there's no way, for instance, if somebody wanted to ask the question, you know, what would happen if this were not about child abuse, but instead were domestic abuse? If we're about, you know, adults instead of children, or if it were a fire hotline instead of a, you know, a child abuse hotline or a suicide hotline or anything else like that. And you can't really get at that, presumably, without doing some study in the real world. Now that you've done this, would you be comfortable advocating for a small number of well-controlled glitches injected, even in sort of sensitive cases, since there's evidence that people are good at disregarding them? Would it be useful for, like, you know, in some other setting to argue for the ethicality of doing that?
So no, precisely because of what you said. That is, we don't know whether the humans being good at disregarding these recommendations is something that expands across settings. And in many settings, the opposite has been found, right? There's cases in which there's evidence of automation bias. There's cases in which whether you adhere to recommendations or not, and that is something that we looked at in the paper I didn't include here, whether it varied depending on demographics of the children, right? In the criminal justice system, it has been found that part of the disparities you observe in the decisions that are informed by the algorithm is because in some states it has been observed that judges' willingness to adhere to the recommendation or to update their prior belief depends the varying on a condition on the race of the defendant or the socioeconomic status. And so because you don't know that, you cannot ethically say, well, let's see what happens if I say that this person is high risk, even though they're not. Are you going to incarcerate this person? Or are you going to not send a social worker to visit the home of someone who may be at risk?
So, I mean, some people might be able to make that argument if you could point to, by answering this question in this other domain, we could create some long-term benefit for our ability to respond in general. But I guess, am I correct that in your study, basically you're saying that there's, we have this interesting information that we can conclude, which is that people aren't completely averse to the algorithm and they're not completely biased towards the algorithm, but you haven't identified a way that knowing that benefits the future, so there's no cost benefit analysis to injecting the glitch. Is that fair to say?
So I think that the reason why you cannot inject the glitch is the same reason why we cannot do certain, things that we consider unethical in medicine just because it would be beneficial for the larger population. But I think that there's still ways, I think, in which we can look at whether there's automation bias or algorithm aversion, right? And so, for instance, I think that looking at meaningful endpoints. So what happened after a certain period of time? Typically, what we care about is not just the observed outcome that we're predicting, right? But there's certain outcomes in a longer period of time that we care about. Healthcare is a space that has done a very good job at establishing what are meaningful endpoints that we should be measuring, right? And so I think that studies that span a longer period of time and look at what happened with respect to other endpoints could look at things like that. So I think that the point here is algorithm aversion automation bias exists, but we shouldn't let that disincentivize us from building systems with a human in the loop. We should just take this combination of results to say how you build a tool, everything that is going on in there may affect whether the humans are making good use of the recommendations or not. And we need to and some researchers have already pointed at some elements that matter here, but we really need to pay attention on what are those elements, and as you point out, how they may vary across domains to make sure that especially we have a lot of legislation right now that throws a human in the loop as a way to say, well, now this is going, we're gonna safeguard any issues. And so if that's what we want to do, we need to make sure that we're building systems in a way that that human in the loop is actually capable of making good use of those algorithmic tools.
And I guess Jamie, do you want to chime in here?
Yeah. So one point I wanted to make, maybe in response to Peter, I don't know whether it was in response to Peter or Maria, but one thing that makes sense from my perspective is it's true that people will have different types of aversion or affinity towards believing these algorithmic predictions, and that might depend upon all sorts of characteristics of the people that they're making decisions about. But one thing that could be done in the name of understanding sort of that the type of that algorithmic aversion or bias towards might be for there basically to be an external like 1% validation set that's happening on top, right? And if you did it in a lab or if you told the judge, they'd behave differently. So you can't do it that way, right? You have to basically say that there's going to be a randomly selected 1% of these things that are going to be audited externally after the fact, right? Like and that might be sort of the best of all of these worlds in that like the judges they might change their behavior knowing that 1% of their cases will be audited or maybe like taken aside for a special review or something, but it's not a big enough percentage, nor are they aware enough of it that they could like, you know, perhaps that's the thing you'd want to do.
Absolutely. Yes, that's a great idea.
Okay, everybody. Well, we're over time here, but thanks again to Maria and to everyone else for your questions and the interesting discussion.